Okay, so here we go. In the same exact position and everything. I just wanted to break it up, and we'll talk about Fibonacci, and then we'll probably be done with today's content. So as I look at it, what I see is this. I mentioned earlier that the English knights, they have to come through here, and probably they're coming across Italy and on their way to the Promised Land, to the Crusades. And Leonardo of Pisa, that means that's where he's from, right? And Pisa is a city in Italy. So what's happening is that the English knights, I mentioned that they might run short of funds, right? Okay, they have to go through Italy, and as they're going through Italy on their way to the Holy Land, sometimes they need loans for war. I'm going to have to feed my horse. I'm going to have to feed myself. And so what we see is that bookkeeping for these particular, for the knights in particular, people in the Crusades in general, bookkeeping is really important. And interestingly enough, when we come upon Leonardo of Pisa, he is an accountant. Okay, so he knows all about keeping books and pluses and minuses and all of those kinds of things. So he actually kind of runs across some of these Hindu Arabic numbers, and it's believed that the way he came across it is because some of these knights, English knights in particular, brought back particular books from the Arabs, and they needed loans for the war, and so they traded. Okay, so traded with Fibonacci. And so what he saw, because he's an accountant, is he's looking at things like Hindu Arabic numbers for the first time. Untutored, unschooled, everything, all by himself. He's looking at these Hindu Arabic numbers. He's seeing the way that they can be used, the processes, the arithmetic, that kind of thing. And what's he doing? But he's comparing it to, look, he's in Italy, Roman numerals, right? Who's in Italy? Roman numerals. Okay, so think about taking Roman numerals and adding them and subtracting. We had to do this, right? Multiplying and dividing. Taking a square root with a Roman numeral. We didn't even do that, right? Because it's just so complicated and unheard of, and it's just cumbersome having those Roman numerals. So he sees, hey, look, these people, Al-Khwarizmi in particular, these guys, they're doing like more advanced math even with these Hindu Arabic numbers than what we could possibly be doing, right? Okay, so who is this Fibonacci guy? He's in Pisa. He comes from a trade family. His actual name is Leonardo Bonacci. Okay, his family is Filio Bonacci. Okay, so this is where Filio Bonacci, okay, that gets shortened into Fibonacci. Okay, and that's how we get his name, basically. It's kind of a mixture of his last name with other words, basically. Okay, so what does he do? He writes a book. And what is that book called? It's interesting. It's called The Best of Hindu, Arabic, and Greek Methods. Okay, The Best of Hindu, Arabic, and Greek Methods. And he brings these things that we were seeing over in, well, for first Greek, and then it goes over to the Arabic countries, and he brings them back to us. And what ends up happening is, because he sees the best of these things, he starts incorporating different methods, different processes, and he starts showing algebra and geometry and proofs. Proofs, oh my goodness, we haven't seen proofs in a while, right? That wasn't since the Greeks were around. So he starts doing all of these things that perhaps we haven't seen in the past, and starts bringing it out in a method that people will be able to see it and understand it, and starts bringing it to the forefront for people to see. All right. So he earns, by doing this, by bringing all of these things together, he earns the title from several areas of the first great mathematician of the Christian West. And most people probably know his name, at least most math majors for sure probably know his name. They've heard of Fibonacci before. One of the things that he does is he writes a book that's called Liber Abaci. And this one's actually interesting to me because it's got that Abaci part in it, right? And I think, oh, Fibonacci, Bonacci for his last name. So in Webster brain, I just automatically attach that to Fibonacci. However, it does not mean the book of Fibonacci or whatever I might be thinking it is. Instead, it means the book of the abacus, which is also interesting because that maybe pulls some really, really Eastern stuff in, like Chinese mathematics and different things like that. So that's what his book is called. It was written in 1202. And inside of it, what he's got is calculations. He's got computations. He's got arithmetic. He's got fractions. Oh my goodness, look at these fractions using our Arabic numbers, 5/7. And the Romans didn't necessarily have the problem of notation that the Egyptians did as far as wanting to use unit fractions, but really, if you're using Roman numerals, are you doing fractions that much? Not so much, right? So look at these lovely fractions that we can do with these Hindu Arabic numbers. He worked because he was in the trade, a family of traders, and because he was actually an accountant. He worked what he considered to be merchant problems. And these merchant problems, he turned them into recreational problems. So, hey, you're sitting around not doing anything. Why don't you work on, Susie wants to trade a bunch of olives kind of problem? It's a real world problem. Maybe we can relate it to our own personal lives, that kind of thing. And hey, yeah, this could be useful to us. So just for funsies, let's go work some recreational problems. That's what he was doing. Okay, an important piece of information. He was supported by the Holy Roman Emperor Frederick II. Okay, he was supported by the Holy Roman Emperor Frederick II. So he is being state sponsored. And so he must be a great mathematician, right? He's the first great mathematician of the Christian West. So that's interesting because that means that his learning was paid for by the emperor. Really kind of cool. He was in the employ of Frederick, and as such, when he was older, of course, he was expected to produce, as you might be expected to produce if you're being employed by the Holy Roman Emperor. And one of the things that Frederick asked of him was to go negotiate a deal with the Muslims over Jerusalem. Remember, this has been going on since about 1000 AD. This guy we're in 1200s basically. So there's been a couple of years of war going on over Jerusalem. And Frederick says to Fibonacci, hey, I know you're a mathematician. I know you're an accountant. I know you come from a trade family. Maybe you don't have a ton of qualifications, but maybe all of those give you a specific insight and a specific ability to go and negotiate a deal with the Muslims. So I'm sending you, please go do this. And what he did, it's actually interesting. He made a peaceful deal with the Muslims for the Christians to take over Jerusalem. Now that's interesting, right? Made a peaceful deal for the Christians to take over Jerusalem. And what he said was, so we can cohabitate basically. What we're going to do is it's going to be in Christian control. But the Muslims can come and visit. Okay? You will have access to all of your holy places. So if there's a shrine here, if there's a particular idol or something like that you want access, let's negotiate it. Let's figure out what your holy places are, and we'll maintain the control of it. We'll kind of run the city, but we will let you come and go, and we'll share, basically. I know that's a novel concept. We try to teach our children, very young children, to share, right? And it takes hundreds of years of war for us to get to that point. But here you go. That's what happened. So interesting stuff happening here. So he was able to do that and peacefully and make that deal and have both sides abide by it, which is really, it's a feat, right? It's an act of diplomacy that clearly had not been considered before that, so that's interesting. In 1225, Frederick wanted to show off his mathematician, so he organized a math contest. Okay, and he wanted to show how amazing Fibonacci was, basically. So there was a problem that was posited, and it went along the lines of this. Find a number. We'll call it x, such that x squared plus 5 and x squared minus 5 are both squares. Okay, x squared plus 5 and x squared minus 5 are both squares. So here's what was kind of interesting about Fibonacci is he said, okay, yeah, I can do that, no problem. So he works it out and he gives an answer, but no work to this math competition. Okay, So sure enough, he's right. And there's no work attached to it. So they figure out, yeah, we can follow that enough to figure out that your two numbers are both squares, but you're not giving us any help for how in the world you came upon this. So later, what he does, Fibonacci, is he publishes Liber Quadratorium. Liber, Liber, which just means book. Quadratorium, Quadratorium. Liber Quadratorium, which is Book of Squares. Okay, so what he says is inside of this he gives a full detailed description of his solution. Full detailed solution. So he works it out and he's like, hey, here's what I did. Okay, and he calls them proposals or propositions, and he says proposition number 1, you find two square numbers. Or problem number 1, find two square numbers which sum to a square number. Okay, we actually have had a little bit of working with squares, and so maybe we've seen some stuff like this. And so here's what he did for his solution. He says, okay, here's my proposition, and here's my solution. What you're going to do is you're going to find an odd square number. Okay, well, we can do that, right? 9, for instance, is an odd square number. And what we're going to do is we're going to sum up all odd numbers which are less than up to that number. The given odd square number. Okay, that's what we're after. So sum up all of the odd numbers which are less than the given odd square number. Now, we're only talking positives here, right? We're not going to deal with negative numbers. So what he's saying is when you do this and you sum up all of these odd numbers that are less than that square number, the sum is also a square number. That's what he has figured out. All right, so it's kind of a number theory problem if you've had a number theory class. So that's what he's working with. So let's just do one and talk about it for a second. So how about the one that I just mentioned? How about 9? Okay, 9 is an odd square number. Everybody agrees, right? I hope. Okay, so what I'm going to do is I'm going to add up all of the odd numbers that are less than 1 plus 3 plus 5 plus 7, less than 9. Okay, so whenever I do that, I've got 10 plus 6 is 16. Hey, look at that. Sure enough, 16 is indeed a square number. So, okay, now I have two square numbers, but that's not quite what the problem asked for. Let me get it back here real quickly. I have two square numbers. I have my original 9, right? And now I have 16, which happens to be the next square number, right? Which is interesting. And what it says is find two square numbers which sum to a square number. So we have to check it and say, okay, well, do they sum up to a square number? And sure enough, whenever I come down here and I say 9 plus 16, I get 25. And sure enough, 25 is also a square number. Okay. So by using an odd square number and adding up all those odd numbers less than that odd square number, I can get my next square number, And by doing that, then I can say, hey, let's add these together and I'll get a square number still yet. So I don't know. Let's see if there are others that we can do that with. For instance, well, 25 is a square number, right? Odd. So he can be my original. Okay, well, I'm going to have to add up all of the odd numbers up to 25, so maybe I picked a big number, but that's okay. So 1 plus 3 plus 5 plus 7, 9, 11, 13, 15, 17, 19, 21, and 23. It's not amazing, but it's not terrible. And whenever I add all of those together, I get 144. Which sure enough is a square number. Now, earlier in the semester, we actually talked about that the Pythagoreans knew this, right? They knew that if I start adding odd numbers, okay, 1 plus 3, I get a 4, that's a square number. 1 plus 3 plus 5, I get a 9, that's a square number. 1 plus 3 plus 5 plus 7, that's 16, that's a square number. So they knew that they were doing this and they were going to get that, right? The next one is 25, and then 25 plus 11 is 36, and so on, okay? So we already knew this from a while back, but the interesting thing is that what Fibonacci's doing is he's taking this little factoid that the Pythagoreans already knew. He's figuring out how to get to another square number, which is not right next door necessarily, right? 9 and 16 were really close to each other, but look, these have got a big spread in them, right? And whenever he added them up, what he sees is 25 plus 144 gives him 169. And sure enough, that's 13 squared, right? Square number. All right. So really, really interesting. What he said is the sum of consecutive odd numbers starting with 1 is always a square number. We already saw that a little bit. I'll give you, you can play with that a tiny bit if you want to. We may have even proven that earlier. Sum of consecutive odd numbers starting with 1 is always a square number. I think we may have proven that. If not, you can think about it. What it looks like is 1 plus 3 plus 5 plus 2n minus 1. Okay, because I'm going to the guy that's just right below. Okay. Right below where I am, and whenever I add all of that up, I'll get n squared. So in other words, let me show you here. In this case, I added the 1, 2, 3, 4, the first 4 odd numbers, and I get 4 squared, right? So that's how many n's I have. Here I added 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, the first 12 odd numbers, and what I get is 12 squared. So that's where we're getting the n squared from. This 2n minus 1 thing, that comes from the fact that we're adding odds, right? So if I want the first odd number, I put in a 1, 2 times 1 is 2, minus 1, I get 1. If I want the second, and again, you'd have to keep track of sequence numbers versus term numbers, but this would be, what do we want to call him? Odd sub 2, for instance. This is my second odd number. If I want him, I'll put in a 2. 2 times 2 is 4, minus 1, that gives me the 3. If I want this guy, that's odd sub 3, the third odd number, put in 5. 2 times, I'm sorry, put in 3. 2 times 3 is 6, minus 1, I get a 5, right? So that's how we're getting our numbers. If you don't remember, we played with sequences earlier in the semester a little bit, so hopefully that's kind of coming out and reminding you. Okay, so there is a little bit of an interesting thing going on here. If you look at this, then I'm not going to do a whole lot with this, but if I think about 2n minus 1, the guy before this, 2n minus 1 squared, if I look at that equation, that's 4n squared minus 4n plus 1. Okay. And then if I play around with that just a tiny, tiny bit, like if it was in the middle of the sequence, I can look at this and I can pull out 2 times 2n squared minus 2n. And I'll have a plus 1. And this gives me something that's in the format of the next number, right? If I was looking at the 2n minus 1 guy, the next guy would be this guy, call him k, 2k plus 1. So it's interesting because there's some interesting number theory-ish type stuff going on in there. So you can just kind of play with that and see what you think. All right. Where am I? 25 minutes. That's 65 minutes. I'm going to go just a little bit longer. I think we can get Fibonacci done, I hope. Let me see. I think we can. So just real quickly for Fibonacci sequence, I think that most people have heard of Fibonacci sequence. It's a very famous sequence. Okay. It's the one about the rabbit reproduction. So the idea from Fibonacci was that if you have a fenced-in, enclosed garden space, okay, and I stick 2 rabbits in there in the garden, one is a male, one's a female, and we'll call that a pair. So I start out with 1 pair of rabbits. And of course they're babies. And the way that, according to Fibonacci, the way that the reproductive system of rabbits went was 1 month they're babies and they can't reproduce, can't do anything. Okay, so for the second month, I still have a pair of rabbits, 1 pair of rabbits, but now they're adults. Okay, and what he said was in their second month, they can breed, but it takes 1 month to have babies. Okay, this is his hypothetical situation. I understand this is not necessarily exactly how it works in the reproductive habits of rabbits. This was just the way he came up with it, because he was looking for some sequences and different things. Okay, so he has this second pair, or he still has 1 pair of rabbits, right? But in the 3rd month, now he's going to have 2 pairs of rabbits. Because according to Fibonacci, he still has the 1 pair of adults, but now they've had a set of babies, so he'll have 1 set of babies. Okay, so that's his idea. 1 pair of adults and 1 set of babies. Now next month, what's going to happen here, these adults, they're going to breed again. It's going to take 1 month for them to have a set of babies. So next month, this kind of turns into kind of a crisscrossy type thing. Next month, this set of adults has 1 set of babies. They're still adults, so they count over here. But now it took 1 month for these babies to grow up, right? So in the next month, I have the original set of adults plus these babies of theirs that reproduced. And of course, in this fantasy world of Fibonacci's, there's just 1 set of babies, 1 pair. That's all the rabbits they had. There's no 8 rabbit litters or whatever. And of course, they are a boy and a girl. And of course, they are going to breed separately from the adults. Okay, so keeping everything separated is the way that they're doing it. So in this next month, the 4th month, what I have is the 2 adult rabbits plus the babies that the original adults had again, right? So that's 3 pairs of rabbits. And so on and so forth. So what we start seeing is this crisscrossy thing. Now that these are adults, all of them can have babies. So next month, there will be 2 new sets of babies. Okay? And it's going to take these guys a month for them to mature. There's already 2 adults there, so I'm going to add 1. So that's 3 adults. Okay? So now for this month, I've got the 3 adults plus the 2 babies. That's 5 pairs. So you can kind of see what's happening here. On a test for this one, by the way, if I wanted you to kind of reproduce what's going on. I have been known in the past to possibly give a table and one row to be, or I'm sorry, one column to be the number of adult pairs, and one column to be the number of baby pairs, and then the total pairs. And if you do it correctly, you'll see a kind of nice pattern that falls out. So what he said was my sequence is 1, 1, 2, 3, 5. And what he sees is I'm always pulling this guy down and I'm always pulling this guy down. So I'm always adding them together, the last two things together. So, because like for instance here I added the 3 and the 2. Those were the last two numbers that I had the 2 months before, right? So that's the idea behind Fibonacci. Most people go, oh, you start with a 1 and a 1, you add those together, you get 2. 1 and 2, you add those together to get 3. 2 plus 3, I add those together, I get 5. So without having to go through all the rigmarole about the rabbits, I can now say, just add the two previous terms. This is a recursive formula, right? 3 plus 5, I get 8. 5 plus 8, I get 13. 8 plus 13, I get 21. I want to do just a couple more. 13 plus 21, I get 34. 21 plus 34, I get 55. Let's do one more. 34 plus 55, I get, what is that? 89. Yeah, okay. Oh, let's do one more. 55 plus 89 is 144. Okay. So, and this is going to just increase forever, and according to Fibonacci, none of them can get out because it's a walled-in garden, and I'm going to have infinite amounts of food, and I'm going to be able to fertilize my food with the rabbit poop, and it's all going to be wonderful. Okay, so no worries as far as anybody dying off or anything like that. They're all alive, they're all healthy, they're all sticking in their pairs. It's awesome. Okay, so the question becomes, what in the world can I do with this Fibonacci thing? Why are we bothering? Well, first of all, I can label it as a recursive formula. In order to do that, what we normally do, the modern day notation for it, is we say Fibonacci term number 1 is a 1, and Fibonacci term number 2 is a 1. And we know that our recursive formula is, if I want to get the next Fibonacci term, what I do is I add together the two previous. So to get f sub n, I add f n minus 1 to f n minus 2. Okay, so I'm adding the two previous terms, and that this will work for every n greater than or equal to 3. So I've got 1 given, I've got 2 given, and then I'll always add the two previous terms for 3 and above. So I'll get f sub 3 by adding 1 plus 2, or f sub 1 plus f sub 2. Alright, so it's kind of a cool growth pattern. It's what we see coming in here. And if somebody wanted to look up Fibonacci sequence or do a presentation, an article, or something like that on the golden ratio and or Fibonacci, they would see some really cool stuff coming in here. For instance, it is said, and I have actually stopped and counted before, that often we can see Fibonacci's numbers, so the 1, the 2, the 3, the 5, the 8, we can see them in spirals. We can see them in seashells. We can see them in seeds on a plant, like a sunflower plant or something like that. We can see it in petals on flowers, and on and on and on. So it's this lovely growth pattern that pops up. In fact, people like it so much that what they have done is, there is a journal that's called Fibonacci Quarterly. And it is actually really interesting because it's been published since 1963. So lots of people have devoted lots of time. It's about 4 times a year 4 journals about 4 times a year since 1963. So it takes a lot to publish that many journals for that many years, right? So it's kind of a big deal, especially in math, especially in the look at natural things in math. And one of the cool things about this particular sequence that people see is it brings us back to the golden ratio, which I mentioned just a second ago. Golden ratio, which is 1 plus the square root of 5 over 2. And if you remember, Euclid had that. That's where we first saw this number back in ancient Greece when he was constructing his regular pentagon, right? I put that construction, the basics of it, on the D2L site. So you can go back and look at that if you would like to. So yeah, Euclid had that number, and he called it the natural number, or the golden ratio. I'm sorry, not the natural number, the golden ratio. And if you go ahead and you kind of calculate that number, what you'll see is that turns into approximately 1.618034. Okay. In modern mathematics, they've even dedicated a Greek letter to it, phi, right? Or some people say phi. So we've dedicated that number to it. So the question becomes, well, how in the world do you see 1.618 whenever you look at this big long sequence? And I'm kind of running out of time, so I don't want to get into it too terribly much. But here is my hint to you to see if you can find that particular number. What you'll do is, let me rewrite the sequence here real quickly. 1, 1, 2, 3, 5, 8, 13, 21, 34. I'm sorry, I'm just out of room, so I'm moving to the next page. 55, 89, 144. So what you should do is you should start by dividing successive numbers. Okay, successive. So I'm going to take the second term and divide it by the first term. Well, that's just 1 over 1. That's a 1. But then if I take the third term and divide it by the second number, 2 over 1 is 2. 3 over 2 is 1.5. 5 over 3, I get what? 1.66666. Repeating, is that right? Yeah, because it's 2/3. So I get this lovely thing. And what we see is, look, I've only done 1, 2, 3, 4 of my ratios. I'm only through the first 5 Fibonacci numbers, and I already have 1.6. Now it's too big because it's repeating 6s, right? But I'm after 1.618. And if you really look at it, what's happening is the first ratio is smaller, the second ratio is bigger. The third ratio is smaller, the fourth ratio is bigger. So what's happening is by doing these ratios of successive Fibonacci numbers, that's what we're doing. By doing this ratio, I'm kind of triangulating in one above, one below, one above, one below, one above, below, one below. And these numbers, these ratios, are going to sandwich in until right kind of in the middle, I'm going to get 1.618. Okay. So what I'd like for you to do, just to play with it and make sure you understand that and that you're prepared for a test, is go ahead and do the ratio 8 over 5 and the ratio 13 over 8 and the ratio 21 over 13 and so on and so forth. Do it all the way through 144 and see what you get as you go through. And I think you'll be kind of impressed. Now for our purposes, because we're looking for the ratio to be 1.618, I actually need for my bigger number to be on the top, right? So make sure that you put the bigger number on top. That will give me a number that is bigger than 1. And I am beyond what I would normally do for talk time. So what I'm going to do is I will wrap up Fibonacci real quickly at the beginning of the next lesson, and we will go from there. Thank you very much. Have a good night.